Alright, today we're going to start talking about solving trigonometric equations. Right? There are the last two sections in the chapter are all about solving different types of trigonometric equations. Okay? So that's the rest of the chapter. So we'll start with some easier ones and then start to progress and look at some maybe more challenging ones. So these are just all the different types that we're going to look at in this section. You don't need to write all these down, right? But we're going to solve basic ones where we just have a trig function equal to a constant. We'll look at factoring trigonometric equations. We'll look at using our identities to write a trigonometric equation just in terms of one trig function. And then we'll look at ones where we're squaring both sides. Right? So let's start with some of the easier ones. Right? I guess it should kind of point this idea out. A trigonometric equation is an equation that has some trig function with a variable in it. And we've talked about an identity already. Right? That's an equation that's true for all values in the domain. But this last bullet is kind of important when we're solving for trigonometric equations. It means finding its solution set. Okay? So most of the time we're going to have more than one answer. And in a lot of cases we will actually have infinite answers. Trig functions are periodic, right? They keep repeating. So what we're going to end up doing is saying, well, this is our solution, but then it repeats every 2 pi. Okay, so we're actually going to write our solutions as, here's the answer, and then plus 2 pi, plus 2 pi, plus 2 pi, plus 2 pi. And I'll explain that a little bit more when we actually get to an answer. All right, so let's start out with some really easy ones. Sine of x equals square root of 2 over 2. Cosine of theta equals negative square root of 3 over 2. And tangent of x equals negative square root of 3. Right, so this first one, sine of x equals the square root of 2 over 2. What we're thinking about is for what angle is this true? For what angle or angles on the unit circle is sine, which is the y value, equal to the square root of 2 over 2. So when we're doing these, it'd probably be a good idea to have out your unit circle. Right? Remember, you don't have to have that memorized for the test. You'll get a unit circle for the test. So I think I heard somebody say one of the answers, 45, or if we want it in radians, that would be pi over 4, right? So one of our answers is going to be pi over 4. Where else on the unit circle is sine equal to the square root of 2 over 2? 3 pi over 4, right? So I just kind of mentioned this idea, okay? The directions say find all solutions. Okay, so these are the two values on the unit circle where that would be true, where the sine is equal to the square root of 2 over 2. However, if I go all the way around the unit circle and add 2 pi, I'll be back in the same spot. So if I add 2 pi to this, I could say 7 pi over 4 would be another solution. Right? No, that's not right. 9 pi over 4, sorry. So if I add 2 pi to this, I'd be at 9 pi over 4. If I add another 2 pi, I would be at 17 pi over 4. And we could keep doing that forever, right? We could keep adding 2 pi onto this forever, and that would still be true. So the way that we express that answer, we say we're going to add every multiple of 2 pi. So we say plus 2 pi times n, okay? And in math notation, n is just understood to be an integer, okay? So I guess for this first solution, Let's write out where n is an integer. You do not have to write that every time, right? That's just kind of understood when you're writing out in math notation that n is an integer. But what this is saying is we want to take 2 pi times 1, 2 pi times 2, 2 pi times 3, 2 pi times 4. And it would also work for negative values. We can take pi over 4 and go backwards around the unit circle, 2 pi, and we would get to the same spot. So we can do the same thing here. Okay, so we end up with 2 solution sets. Right? We can say pi over 4 plus 2 pi n, and then also 3 pi over 4 plus 2 pi n. Okay. Questions so far? All right, how about B here? Where is cosine equal to negative square root of 3 over 2? 5 pi over 6. And 7 pi over 6. Okay. So again, to express all solutions, we take these two and then tack on plus 2 pi n. How about C, where is tangent equal to negative square root of 3? Okay, so this is a little bit trickier because we don't have those values listed on the unit circle. Right? So again, we want to think about tangent is equal to sine over cosine. So for what values of sine and cosine would I get a quotient of the square root of 3? Two pi over 3. I believe that. Alright, so at pi over 6, we would get positive square root of 3. We want it to be negative square root of 3. Right? Now, the nice thing about tangent is that its period is just pi. Right? The period for sine and cosine is 2 pi. So I need to look at the entire unit circle when I'm trying to find values for sine and cosine. Since the period for tangent is only pi, I only need to look at half of the unit circle. Okay? I only need to look at half of the unit circle. So if we can make a note of that, right, we're just looking at 0 to pi, right, just half of the unit circle. And then what that means for our solution set, we can say that it's going to be 2 pi over 3 plus pi n. Right? Since tangent repeats every pi, we only need to look for one solution. Now, I will say that if you look at the entire unit circle and give me the other value, which would be 5 pi over 3, right, that wouldn't be incorrect. Okay? So if you wrote this as x equals, I'll do it like this. So this is one way to express our answer, or we could say x equals 2 pi over 3 plus 2 pi n, and x equals 5 pi over 3 plus 2 pi n. Right? If you forget that tangent repeats every pi, that's actually okay. You could just look at every place where this is true on the unit circle and express your answer like this. This answer and this answer actually give you all the exact same values. Okay. Does that make sense? So we can either say tangent repeats every pi, or we could find both values and say they'll just repeat every 2 pi. Questions so far? Bless you. How do I get rid of all those? Alright, let's try one like this. Okay, find all solutions where we've got a few extra things going on in this function. Right? 2 times sine of x minus pi over 4 plus 1 equals 2. Okay? For a problem like this, the first thing that we want to do is isolate the trig function. Okay? So that means get rid of anything that's on the outside of the trig function. So I want to get rid of this plus 1, and I want to get rid of this multiplying by 2. So I'll start by subtracting 1 over. If I subtract 1 over, I will have 2 times sine of x minus pi over 4 equals 1. Then divide both sides by 2, and we'll get sine of x minus pi over 4 equals 1/2. So now, very similar to what we just did on the last problems, I want to go to my unit circle and see where sine is equal to 1/2. So on the unit circle, where is sine pi over 6? And 5 pi over 6. So what we're going to do is take whatever's on the inside of the trig function and set that equal to these 2 values. So I'm going to have x minus pi over 4 equals pi over 6, and also x minus pi over 4 equals 5 pi over 6. Now, just one step to get x by itself, add pi over 4 to both sides of the equation. What's pi over 6 plus pi over 4? How would we do that? Calculator? We could do this by hand, right, with just getting common denominators. So pi over 6 plus pi over 4. The denominator, common denominator, we could make 24. Sure. So I could make this 4 pi over 24 plus 6 pi over 24. 10 pi over 24, which we could actually reduce. Both of those are divisible by 2, so 5 pi over 12. So I can say x would equal 5 pi over 12 for one of my solutions. Okay, but, I mean, yes, you could use a calculator to do 1/6 plus 1/4. Okay, then we just want to do the same thing over here. Add pi over 4 to both sides. So again, to do this by hand, we can get common denominators. So we do 20 pi over 24 plus 6 pi over 24. 26 pi over 24, which would reduce to 13 pi over 12. Now, in this case, the directions specify to just find all solutions in the interval 0 to 2 pi. Right? In the last problem, it said find all solutions. So that's why we tacked on the plus 2 pi n. If it just specifies on the interval 0 to 2 pi, we don't need to tack on the plus 2 pi n. Right? These would be the only two answers that are in the interval 0 to 2 pi. Questions? Do we want to try another one of these, or think we're all right? Maybe one more? All right, how about about 2 cosine of x plus pi over 6 equals square root of 3. It works out. Did we get 0 and 5 pi over 3? Questions? Let's take a look at one more type of an equation then. Okay, how about something like this? We've got 2 sine squared minus 5 sine plus 2. Okay? This is just a quadratic equation. Right? If you want, right, we could just replace sine with an x. Okay? All this is asking us to do basically is start by solving this quadratic equation, 2x squared minus 5x plus 2. Right? We're just thinking about solving this first. So how would I start by solving a quadratic like this?
Oh wait.
If you do it first, that might go out.
we want an x factor, right? So we do the first thing times the last thing, which would be 4. So the middle term is -5. So I want two things that multiply to 4 that add to -5. So what two numbers would multiply to +4 and add to -5? Sam? -4 and -1. Right. So we're splitting this up into 2x squared minus 4x minus 1x plus 2. So then we're factoring by grouping. Right? So what we have is we can take a 2x out of this, so we'll have 2x times x minus 2, and then I could take a -1 out of this, so -1 times x minus 2, and then we end up with 2x minus 1 times x minus 2 equals 0. Okay, so what we did at the beginning here, we replaced sine with x. So what we really have right now is 2 times the sine of theta minus 1 and sine of theta minus 2. Okay. So now I can take each of these and set them equal to 0 separately. So I can say 2 sine of theta minus 1 equals 0, and sine of theta minus 2 equals 0. To solve this one, add 1 over, divide by 2, get sine of theta equals 1/2. So just like we've been doing, once we get our trig function by itself, we want to go to the unit circle and see where this is true. Where does sine of theta equal 1/2? Five or six, and 5 or 6. Now, this question says find all solutions. So plus 2 pi n. Now, we want to do the same thing for our other factor. So I would add the 2 over. Get sine of theta equals 2. Where on the unit circle is that true? Nowhere, right? The range for both sine and cosine is just -1 to +1. So this piece doesn't give me any solutions. You say why? Oh, undefined. Yeah, so we could just say this is undefined or no solutions from this part. Okay, so our only answers are here. Pi over 6 plus 2 pi n, and 5 pi over 6 plus 2 pi n. Not necessarily. That's a good question. So Alec asked, is it usually going to be the case where we'll get solutions from one factor and no solutions from the other factor? That's not necessarily true. Okay? We may end up getting solutions from both pieces, okay? But just so that we're aware, it is certainly possible to not get solutions from one of the factors.